Take a look at the climbers at the top of this peak. To find the exact height from the ground to that summit, you wouldn't physically hike all the way up there with a measuring tape. We face this same obstacle with a tall tree. While you can measure small objects using a physical scale, we lack a way to directly touch and measure things that are far out of reach. Engineers and scientists don't rely on physical ladders to solve this. Instead, they use a mathematical workaround to determine the size of the unreachable. This method is used daily by the people who build our world. Architects, civil engineers, surveyors, and pilots all use these calculations to find exact distances without needing to physically reach the destination. This isn't a recent development. Ancient civilizations developed these techniques thousands of years ago to accurately survey land and construct monuments that still stand today. The name for this system is trigonometry. Its Greek roots describe the process perfectly: tri for 3, gon for angle, and metry for measurement. It is the science of measuring triangles. Every calculation centers on one shape, the right-angled triangle. The bottom is the base, the vertical height is the perpendicular, and the long diagonal is the hypotenuse. In the real world, the ground is the base, and the tree forms the perpendicular. Think about what happens if you stay in the same spot, keeping the base distance the same, but you tilt your viewing angle higher. As your viewing angle increases, the perpendicular height grows. The two are mathematically linked. This is the foundational rule. The specific angle determines the exact proportions of the triangle. If we lock our angle at 30 degrees and double the base length, what happens to the height? It doubles too. The triangle is larger, but because the angle hasn't changed, the ratio between base and height remains exactly the same. These proportions are constant. This means we can calculate the height of a massive mountain using the same angular relationships found in a small drawing on a piece of paper. To use this in practice, we need a mathematical way to turn a specific degree of an angle into the exact numerical ratio of the sides. Since these ratios are fixed for every angle, mathematicians assigned names to the different pairings of sides. These names, sine, cosine, tangent, and their counterparts, are labels for those ratios. For example, sine is the name for the fixed relationship between the perpendicular height and the diagonal hypotenuse. These terms provide the bridge between the angle you see and the distance you want to calculate. They allow us to translate geometry into measurable facts. We've moved from a real-world problem to the right triangle, discovered how angles lock proportions, and identified the 6 ratios used to calculate them. Now that you understand why these ratios were created, you are ready to begin using them. Every calculation in this chapter starts here, with the simple logic of a locked angle.